Hi, now we continue with the forecasting analysis, and in this second video we're going to focus on stationary models. In this case, suppose that we tested for a linear trend and we found that the p-value is more than 0.5. Of course, this indicates there's no trend. So in this case, a stationary model is appropriate. And there are several stationary models to choose from to do the forecasting. So one of those models is to pick the last period projection, LPP, or sometimes called the naive approach, where the projection for the next period, ft plus 1, so that's period t plus 1, is the actual for the last period yt. So remember, yt are the observed values of my, say, sales over the last 36 months. So if I want to forecast month 2, it would be exactly what I saw my sales in month 1. For month 3, it would be my sales for month 2. For month 36 would be my sales for month 35. And my forecast for the 37th month would be my forecast for what I observe for Y36. Because I go for Y38, it would be still Y36, because from that point on I don't have any sales data available. So my future forecast all would be my last period. And so that's how I can calculate the error terms. The second model is called a simple average model. And this is the arithmetic average of all previous time periods. So if I want the forecast for period t plus 1, I take all periods yt minus 1 up to y1 divided by t. Because sometimes somebody might suggest that really these two models are that's why they are called naive and simple, because the first one, it just gives you the last period. Well, if just the last period happened to be very low sales or very high sales, these my projections for the future are going to just follow that period. The second one suggests that I should average the whole past to get my forecast for next period. So I'm giving the same weight for last month's sales, giving that same weight as my 30 months ago sales. That's also I should be giving more weight to more recent sales data than to the distant sales data. So because of that, we have this model called the moving average model, or rolling average model. And it's called a simple moving average, which basically the arithmetic average of the last n periods. And it really helps smooth the oscillations, the ups and downs in the time series we have. So ft plus 1, I can take the last period t, the one before it, all the way back n periods, and divide by n. So if n equal 4, then my moving average would look like this one: ft plus 1 equal yt minus 1, yt minus 2, yt minus 3. You see that I have the total of the last 4 months divided by 4. Sometimes also I want to give so this gives really the same weight for each of the 4 months, which is 1 over 4, 1 over 4, 1 over 4, and 1 over 4. So sometimes I may want to give different weights to different months. I want to give again more weight maybe to more recent months. So I can come up with this thing called the weighted moving average. And I have n non-identical optimized weights. And so my ft plus 1 would be, I take each one of the previous month's sales up to n months and multiply that by a weight and add them up. Where, remember, ft plus 1 is the forecast for period t plus 1, wi is the weight for period I, where all the weights should add up to 1, and n is the number of periods in the moving average. So in this model, older data is less important. Weights are often based on experience and intuition, so there's no set cut formula. It's going to be some give and take. So if n equal 4, then the weighted average would look like this: W1 T1 plus W2 T2 plus W33 T minus 2 plus W4 T minus 3 over the sum of W's. And many times we assume that the weights are such that W1 is larger than W2 larger than Wn, and they add up to 1, right? Of course, if they didn't add up to 1 and use this sum of Wi in the denominator, that would take care of that, because W1 over this would be my new W1, and so they would all add up to 1. The exponential smoothing model, and here we're going to focus on single exponential smoothing. Here we use a one smoothing constant alpha, and this model, if you look here, it's the forecast for period t plus 1 is equal a weighted average of the last period, the tth period actual sales, say, or actual observed value, plus multiply that by 1 minus alpha of the forecasted period for period t. So the value for the forecasted value for period t plus 1 depends on the actual value for period t and the forecasted value for period t. So then yt is the actual value, ft is the forecasted value for period t, and ft plus is 1 is the forecast for period t plus 1. Of course, we need to initialize this by saying f1 equal y1. So alpha is a number between 0 and 1. Let's look at some of these comments here. Weighted average is a special form of a moving average in which most recent data is weighted most heavily, which is what we would like to. Weights decline exponentially, giving less weight to periods as the time periods become more distant from the present. And that's because if you really to follow this up, like ft also is going to be alpha yt minus 1 plus 1 minus alpha ft minus 1, and so on. So it goes backward with less and less weight, and the alpha becomes smaller, or the smoothing constant becomes smaller. When alpha is large, greater weight is given to the current period's actual value. So how do we choose a smoothing constant? There are different ways of doing that. One way is to maybe run the model with 10 choices of alpha, starting with 0, 0.1, 0.2, 0.3 up to 1, and pick the one that gives you the smallest forecasting error. We talked about several forecasting errors we can measure, and pick that one. Or here are some rules of thumb for this alpha. Suppose we think the last 4 periods are the most relevant, then we call that k, and we write k equal 2 minus alpha over alpha. If we solve that, alpha would be 2 over k plus 1. Okay. So there are other models for stationary periods, but these are the ones we're going to focus on. And here's an example that I'm going to go over. It's called home water consumption. So we're going to measure home water. We have data on the last 12 months of water consumption, and this is period 1 all the way to 12. The month is January, February, all the way to December. And my monthly water usage in hundreds of cubic feet, that's 17, 24, 21, 20, and so on up to 21. So I want to make a forecast for next year's January consumption. Typically would like to forecast the whole year, but once you forecast January, if you have a stationary model, the whole other month will be the same. So first we test for, so the first thing you want to do for this is test for stationarity. If we test for stationarity using the regression model, we'll find out that our p-value is more than 0.05. So that means we have stationary data and we can run any of the stationary models. Okay, so let's use the naive approach and do the forecasting. And you notice here, although we have the actual values for January to December, we still can forecast those values. And if we use this method, basically February if we use the naive approach, February forecast would have been January actual usage. March would have been the actual February. April would have been the actual March, and so on. And December would have been the actual November. January is the actual December. You notice here that we are in December. We don't have the actual figures for January, but we can forecast them as 21. And so this allows us to calculate the error terms. So this minus this minus this. These are E1, E2, E3, E4 up to E12. And we can use these to find the from the E's, find these forecasting errors. Okay. Now if we use a 4-month moving average method, so the first forecasted value we can do would be May in this case, which is the average of January, February, March, and April, and that gives me 20.5. If I want to forecast June, then I drop January and add May, so I have 4 months and that gives me the same value. If I want July, I drop the February and add June, and so on. So my next January forecast is the average of the last 4 months. 1, 2, 3, 4. Add these and divide by 4, and that gives me the forecast there. So now my forecast error here would be only starting from the 5th month. So this minus this minus this, and so on. So I have these forecast error for these values only, which allows me to calculate all the forecast errors we talked about before, and so on. So I can also here I have a 3-month moving average with weighted moving average, where my weights are 0.6, 0.3, and 0.1. So to get the forecast for April, that's the first month I can do, is to get 0.6 times 21, go backward, 0.3 times 24, and 0.1 times 17. So my weights give more weight to more recent value here, and so on. Same thing, this value would be 0.6 times this, 0.3 times 20, and 0.1 times 18, and get 20.4. And then I can get those. So having forecasted those values where I know the actual volume here allows me to compute the forecast error. Same thing here for exponential smoothing. Again, so first we assume this one would give me an error 0 because we assume F1 to be the same as this one, but that's not a forecast, that's a starting point, initialization. Now this value would be alpha 0.2 times 17 plus 0.8 times the other value 17, so that gives you the same value. This value would be 0.2 times 24 plus 0.8 times 17, so gives me this value. So this value would be 0.2 times this plus 0.8 times this, and so on. So we keep doing that throughout, and we get those forecasted values. So our forecast for January is 19.4. This is another method using a smoothing constant of 0.7. So in this case that would be 0.7 times 21 plus 0.3 times 19.38 to get this value, and so on for the other values. One thing you noticed here is that this forecast is 20.51 for the next month, That's 19.4, 20.4, 19, 21. Of course they look close to each other, but then which one is better? So which forecast? I don't want to use all 5 forecasts, and this is for the future. I don't know what the volume is going to be for next month, my usage volume. So it's a forecasted value. Which one should I adopt, especially when I'm forecasting this for several months maybe? Okay, so want to compare the 5 stationary models for this data set. Each one gives different forecast value. Which one should we use? And to determine which one we should use, we compare the forecast errors. So here is the 5 stationary models. So these are the methods I use: the naive, the moving average, weighted moving average, exponential smoothing with alpha 0.2, exponential smoothing with alpha 0.7. So which one is better? Let's see. Using the MSE as a forecast error criterion, which one is closer to 0? Which forecast error is best? Seems to be here. It seems like moving average. This is the lowest forecast error using this criterion. What if I use MAD? That also seems to be better. This comes, the weighted moving average is close second. If I use MAPE, this seems to be the best. This also close second. Wow, so there's some consistency using all these different errors. Sometimes different errors will give you different preferences, so you have to specify which forecasting error is most relevant to you. And the same thing here. So based on these error terms, this is the lowest error in each category, and so my moving average would be my best forecasting technique, and that's the one I would use in the future to keep forecasting my water usage. Okay. So next we're going to look at trend models, and to look at curve fitting time series using least square regression model. So we know if our data suggests that we have a linear trend, then the model we use is the regression model, where ft is the forecasted value, this is the y-intercept, this is the slope, and we use t as our independent variable, and the epsilon here is the random error. Just go back and review to make sure you know how do we verify if a trend is present. And we run this model. There are videos on how to run these models using Excel, so please review these. The next topic is models with seasonality, which will be my next video. Okay, see you in the next video. Thank you. Okay.